Hello and welcome to this video about data structures or types. In this video, we'll investigate polynomials and how to represent them in computers. And here's a short list of the functions that we'll be defining, which are the simplest for polynomials. Firstly, we'll need a way to store the polynomial itself, and this will be done by using these two attributes. The degree attribute shortened to deg, which is the highest power of the polynomial, and its list of coefficients, which is stored in an array called coef. So, for example, this polynomial will be stored in this way. Its degree, which is its highest power, will be stored in pdeg, and in this case will be 3, and the list of coefficients will be conveniently stored in this array. In the case of this array, the coefficient of x raised to the power of I will be accessed by the number I, which is very convenient and makes the code easy to follow. The polynomial will have a lot of functions associated with it, because there are lots of things that can be done with it. We'll start with the addition function, because it is the simplest and therefore the easiest to understand. We'll assume that P has a greater degree than Q. There is no loss of generality, since they can be easily swapped. So this is what their sum is, just their coefficients added together. For coefficients of x raised to a number greater than m, the coefficients are just equal to the coefficients of P, since the coefficients of Q may be taken to be 0. And this is what the subtraction function looks like, which is very similar to addition. So it should be noted that we've lost this loss of generality for subtraction that we've had for addition. Another thing to note is that with addition and subtraction, the degree may become a lot less than what it was for either P or Q. This only happens when they have the same degree, which may be shown in the next example. So I'll just move things up here to make more space. Take, for example, these two polynomials that we'll add together. We'll add them together like this. And this is the sum. You can already see that this sum has a degree that's less than the two polynomials that were added together. This is because their leading coefficients added together to make 0. Two polynomials are capable of being added together to make a constant, which is a polynomial of degree 0. So we have to look out for this when we make the addition and subtraction functions. So this is the degree of the sum, and this is the minimum of the degrees of the two polynomials that we added together. So if we're going to make a polynomial add function, we'll need a zero eliminate function to decrease the degree of the polynomial if the leading coefficient becomes equal to 0. This is the strategy for making the zero eliminate function. If we have a polynomial with its three leading coefficients being very close to 0, being represented by epsilons, we'll have to decrease the degree of this polynomial by 3. This is how these coefficients called epsilon are shown close enough to 0 so that they can be treated as though they were 0. And this is the output of this function to remove these three coefficients. So this is how we'll create the polyadd function. We'll set the polynomial r to be the sum of these two polynomials. We'll assume that n is greater than m without loss of generality. The degree of the sum is equal to the maximum of these polynomial degrees. We'll create the first loop, which sums up all of the coefficients of these two polynomials. In this next loop, all of the coefficients of the sum are equal to the coefficients of the polynomial with the greatest degree. So here's how to implement the zero elimination function. We'll implement a loop to go through the entire polynomial. And we'll set each coefficient to 0 when it is close to 0, and epsilon here will be equal to a very small number like 1/1,000,000th. Now we'll set this index variable to be the degree of the polynomial, because we want to start the loop from the leading coefficient down to the constant term. And in this loop, we'll keep looping downwards until we get to a non-zero coefficient. And we'll set the degree of this polynomial to this new value. We'll only call this function if the degrees of the two polynomials that we're adding together are equal. Now to have a quick look at how to perform the subtract function for polynomials. We'll set different variables like we did before for addition. We'll have to get the maximum and minimum of these polynomial degrees. We'll subtract all of the coefficients up to the minimum of these degrees, similarly as for addition. We have to do different things depending on which polynomial has the larger degree. If p is larger, then we'll just copy in the coefficients for the remaining part of the polynomial. But if q is larger, the negatives of these coefficients are copied into the remaining parts of these polynomials, because it is being subtracted. So now to look at how to implement the multiplication function, which is harder than addition. We'll set r to be the product of these two polynomials. The degree will always be the sum of the degrees of the polynomials that we're adding together. No zero elimination function will be needed here, so in this sense multiplication is easier. It is important to note that each coefficient of the polynomial r is equal to this in terms of the polynomials p and q that we're multiplying together to get r. Each of the terms whose power of x is equal to I plus j add together to make this coefficient of r. So now we can write it out in sigma notation. We can manipulate all of the dummy variables to write out this sum in this tidier form. So now to write out a sketch of a computer program to get the product of two polynomials. We'll set polynomial r to be this product. We'll get the degrees of p and q and set integer variables to be equal to them so that all of the loops that use them can run faster. We'll set the sum of these two degrees to be equal to the sum of these two variables. We'll initially set all of the coefficients of r to be 0 because we'll sum them up during the next loop. And these nested loops find all of the coefficients of r according to this formula written in sigma notation. Now to create a polynomial that acts on a real number, like a function, returning a real number back, as shown here. We can rewrite the polynomial in this nested form here, so that separate powers of x need never be calculated. And for the computer code, we'll set total to be 0, because we're going to add numbers to total as it goes around the loop. And this loop calculates the polynomial acting as a function on a real number, so as to return another real number. And now to look at some polynomial calculus functions. This is the first derivative of a polynomial. It is fairly straightforward. Just multiply the coefficient by the power of x, and then make it the next lowest coefficient. And this is the computer code which does this, according to the derivative rule for powers of x. And this is the second derivative of a polynomial. You just take the derivative of a polynomial twice, and you end up multiplying the coefficient by 2 powers of x. So this is the code which has a loop that mimics this rule. This is the antiderivative of a polynomial, which is the opposite of the derivative. It can also be called the integral of the polynomial. The constant term is indefinite and can be equal to any real number. We usually set this constant c to be 0 because it reduces the amount of computations. So this is the code which produces the antiderivative, and the constant term is set to 0 at the end. Here are the functions to add and subtract polynomials written in JavaScript. The very slight differences between them have green rectangles drawn around them. Here is the zero eliminate function, which is used after polynomial addition to get rid of coefficients that have a value of 0 and could possibly cause the polynomial to have a smaller degree. I've also written the multiplication function here, which has a complicated rule which can be written as a double loop, that doesn't take up much room. Here's the polynomial evaluate function, which evaluates the polynomial for a particular value of x, like a function. I've also shown the input and print functions. I've explained them in more detail in the permutation data types. In the input function, the polynomial is entered as a string and is changed into an array by the split function to make it easier to work with. Here are the three calculus functions that use loops to perform the differentiation rule for powers of x. So I'm only doing these functions in this video. Polynomial division is much more complicated, and I'll do that in a future video. So I hope that you have enjoyed this video and have felt that you have learnt something from it. Please click like and subscribe if you did. Please leave some helpful and constructive thoughts in the comments, and thanks a lot for watching.